we got a good number. We got 16. I like the number 16 as a rule. So with that, I think we'll just get started. I first wanted to get a poll, just ask everyone real quick, have you guys worked with Arduinos before? Because I'm not really sure. I know boot camp this year has been a little tough, but I wanted to get a poll of like, have you guys worked with Arduinos or other microcontrollers before? So if you could like raise your hand on the, the participant screen if you have, that would be great. Okay, we got a few hands. It's not a requirement, of course. It's just a question so I can get an idea of where the group is at. Yeah, all right. Yeah, this has been boot camp. Usually in boot camp, you can almost guarantee, like, typically we would almost guarantee that you'd be working with Arduinos, but this year where it's so hard to do any work of substance, it is difficult. So I've titled this lecture Microcontrollers, Arduino and Beyond, because we're going to start talking about Arduinos because they're ubiquitous and familiar and all of that. And then we'll segue right on to some other varieties of microcontrollers. So to answer the burning question, what is a microcontroller? I think the easiest way to explain it is that you've stripped down a computer to its very basic fundamental parts, and you stuff it all together into a single chip. And you can imagine, of course, you lose orders of magnitude of processing power. And so you'd think, that's kind of undesirable, but you also gain a lot by doing this. Real computers, I mean, what you really gain with microcontrollers is that it makes it so much easier to interact. You're so much closer to the hardware. That's the way I like to put it. You're close to the hardware. So when you write software for a microcontroller, you're just a hardware abstraction layer away from, writing directly to the input and output pins. Whereas real computers, they're more complicated and it's much harder to get that low level input output behavior. So let's talk about the Arduino Uno, which you may have heard of. I've got a little diagram of it over here. The star of the show on this guy is really the ATmega 328. That's the microcontroller part. And then the rest of this board is all just, there's some power management stuff over on the bottom left, and then there's all the headers where you can plug wires into. And a fun fact is that it actually has a second, Arduino-esque thing on it, which is that little chip up next to the USB connector. And it's another ATmega chip, and what it does, it just bit bangs the USB protocol, because you don't actually have a USB controller built into any of there are some ATmegas that have a USB controller, I think, but I'd have to check. What is bit banging? Yeah, bit banging just means that you're using software to write to the I/O pins instead of using a dedicated controller that writes to the I/O. So it's like, you may say that's a real, because let's say you have, yeah, cool, okay, yeah, that's what bit banging is. So instead of having a USB controller where you write a packet into a register and then a controller handles the protocol, you have to handle that USB protocol in software. And that's fundamentally what bit banging is. So it's like, I don't know why they did it that way. I think they just wanted to stick with Atmel, now Microchip, but they wanted to stick with the ATmegas, and they didn't want to use some other kind of USB controller. It was probably just cheaper to do it that way. So that's what they've done. Just a fun fact there. Another significant thing about the Arduino is that it actually has something called a bootloader. And this is a special little piece of code that somebody, at a factory somewhere has programmed into the Arduino, which allows you to upload your programs more easily so that you can actually upload them over the USB interface. Without the bootloader, it's a little, you can definitely program it. You program it with the in-circuit serial programmer, but that's, it's a little more of a pain in the ass. It's nice to have the USB and the bootloader, but a lot of microcontrollers that you work with, they won't have a bootloader. And, there's also reasons why you may not want a bootloader, because you don't want to sacrifice that little bit of memory or storage rather. Or you might want your own bootloader so that you can program it over some esoteric programming interface. So things to think about. So let's just talk about what I've pulled right from the data sheet, this block diagram of the ATmega 328. And it looks like there's a lot of parts, which there kind of are. And remember, they're all stuffed onto one chip, which is part of the magic of a microcontroller. But, we have all the basic parts of a computer. We have the storage, which stores your files and stores your programs and everything. You have some RAM, which stores stuff that has to be loaded for running the programs, so that you can read and write very quickly and frequently to it. You've got a CPU, just like a real computer. You've got a CPU which has an arithmetic logic unit and working registers. Again, it's simpler and it has a lot, orders of magnitude less power than a fully fledged computer, but you still have a CPU. And something you don't have, well, you do have it, but it's different on a real computer. You have this I/O stuff that you can interact directly with. And you can see they've got arrows going through the dotted line, which basically that indicates that it's going to the physical GPIO pins. So by reading and writing to these registers, you control the input and output pins. Now that's fundamentally what you do in a microcontroller. At the end of the day, what makes things happen in the real world is a reading and writing to registers, which changes the state of the GPIO pins. That's where the rubber meets the road, in a sense. So I think that covers, there's a simple example of a simple microcontroller. So with that, I would like to move on to a different slide deck, which is I've titled Beyond Arduino. I think the Arduino is nice and easy to work with, and it's quite versatile. Why would you may ask, why would I bother to use something else when a microcontroller, or an Arduino rather, is perfectly sufficient? Well, let's try. What I hope to do here is learn the difference between Arduinos and another family of microcontrollers called the STM32s. And we'll move swiftly forward talking about STM32s. We'll learn how to work with the STM32s and learn some hardware design basics. All right. So here's a little comparison. Arduinos are a family of microcontrollers, not just the Arduino Uno, of course. They're dev boards that use microcontrollers made by Microchip. That's basically it. Previously, Microchip bought Atmel a few years ago. So they used to be Atmel, but they kept the name, ATmega and whatever. They use some kind of 8-bit instruction set, RISC architecture. So what it means is every the ALU, that's the arithmetic logic unit inside the CPU, is only 8 bits wide, instead of, so you can only feed it in 2 8-bit numbers, then it, does some computation on those and spits out another 8-bit number. And that's kind of limiting, or can be limiting, because if you're, you software folks might be thinking that, an integer, the integer data type is 4 bytes wide. That's a 32-bit number. So how can you do a computation on a 32-bit number with an 8-bit ALU? And the answer is you have to break it up into multiple computations and then piece it back together, which is kind of inefficient. But the STM32s are based on on a 32-bit architecture. So they take their ALU as a 32-bit wide input. So you can actually process, an integer in a single clock cycle. Well, sort of. Effectively, you can do a simple operation on an integer with a single clock cycle. So yeah, the other thing that Arduinos have are very basic peripherals. They don't even have that USB peripheral. They have to, offload that to another little Arduino that bit bangs the USB protocol. Whereas with the STM32s, you actually get a huge array of different peripherals. And we'll talk more about some of those at some point. The Arduinos also, they run on 5 volts, which might be nice. STM32s just happen to run on about 3.3 volts. So it's different, but that might be a deal breaker for you, but chances are it's not. The trade-offs are, we'll talk about those. Arduinos are pretty cheap, and STM32s maybe less cheap to implement, that is. The individual chips themselves actually probably cost about the same if you're buying them, from a distributor. You also have the Arduino software ecosystem, which makes it really easy to program Arduinos. You don't really have that for STM32s. However, as we'll see, it's really not that hard to break into STM32s. We'll see that in a moment. Arduinos are good starting points. I highly recommend them. I think they're fun and useful. But STM32s have a nice range of capabilities for advanced use cases. So that's what the lecture is going to be about. All those why you might want to use an STM32. So let's go into the wide array of parts that are offered. In an Arduino, you're locked into, there's a handful of parts that you're going to end up using if you go with an Arduino. But with the STM32s, there are, I would wager there are thousands of different parts. And there's some key considerations to have. And one of the big ones is what peripherals does it support? Because I want to, what if I need that USB interface and I don't want another chip? Like, I don't want to have this little Arduino chip or an FTDI chip to handle USB, and I need a USB peripheral. Make sure that my microcontroller has that. Then you also want to look at how much flash it has. The flash is where you store your program, and the RAM. RAM is usually less of a critical resource, as you'll find. But in my experience, if you have less than 32 kilobytes of flash, it's not worth it and you should ditch it. Now, interestingly enough, the Arduino only has 32 kilobytes of flash. And you can do a whole lot with that, but when you're trying to do something more complicated, 32 kilobytes is usually just not enough. So, it's worth it to pay another 50 cents to double your flash memory. It's just worth it. So then you look at the frequency it can run at. if you get a higher frequency, it means more instructions per second, but it also has a higher power draw. So you may not want that. And a lower frequency is slower but lower power. So an Arduino runs at whatever frequency your crystal is at. I don't know the maximum. I think the maximum might be like 24 megahertz, if that. Usually they run on 16 or either 8 or 16 megahertz. Whereas the STM32s, the external crystal will be at like 8 megahertz, but they have an internal phase locked loop that will boost that frequency up to something higher that's more usable. So you can see in this little chart on the left, they give you the frequency of the core. Some of these over on the far left are like, 32 megahertz, 48 megahertz. Then over on the right and the top under the high performance section, you see some that are like 480 megahertz. I mean, that's a respectable frequency for a little system on chip. Sorry, well, it's not really a system on chip, but it's approaching that. That's a respectable operating frequency. You can do quite a bit of computation with that. So then you want to look at, what features does my Cortex itself have? The ARM core inside the RISC architecture. What features does it have? And it mostly affects speed. If speed is really critical, chances are it's going to be an M4 or higher, and it's going to have more computing power. It can run faster, and it has things like a floating point unit, which will do floating point computations in hardware instead of doing them, offloading that to software, which I could talk more about if you have questions. And then another fundamental one is GPIO requirements. How many of them do you have is the question, and that's with an Arduino, you're pretty limited because you can get some parts that have more pins, but typically there's not all that many pins. Even a lot of the lower end mainstream parts of STM32s, even those tend to have at least 30 GPIOs, whereas the Arduino has far fewer. Do I have a picture of an Arduino? I don't, but like it's got like 13, it's got like 20 GPIOs, the Arduino, whereas like even a low end STM32 will have like 30. So now I've got some links here that you can check out later. For searching for a microcontroller, I'd highly recommend some kind of parametric search. If you're looking for a distributor, DigiKey has nice parametric search tools. We can check those out later if you like. So here's a popular choice. I did say that STM32s tend to be more expensive than Arduinos, but here's an example of that being not the case if you know who to buy from. This is a very popular one, the F103C8T6. It's a good balance of cost, size, memory, peripherals. It's popular because of that. And you can buy one of these little dev boards, which has all the clock stuff. It has a linear regulator. It's got a USB interface. You can buy it for about $2. So, it can be programmed somewhat with Arduino, but I don't recommend that just because you can do a whole lot more using the vendor provided tools. Okay, so when you go to a lot of this lecture is going to now talk about how you would design hardware with the STM32s. Or are there any broad guidelines for determining how powerful a CPU you need for a certain program? That's a good question, and what I would want to say is I think a lot of that will come with experience, and I think it depends on the kinds of computation you're going to be doing and how fast, how fast it has to occur. So I think if you plan to do things with floating point numbers, that's going to be a thing that's computationally intensive. Even if you have a floating point unit, well, that's even better. But floating point operations are, typically computationally intensive. So you have to think about that. And you have to think about how quickly you need the microcontroller to respond to some external stimulus. That's another big consideration. So if you've got, if there's some kind of limit switch, or probably not even a limit switch, you're probably thinking of, like, say you have 10 devices that you need to control, and each one has a little interrupt signal that will signal you to read data from that device. You'll be hard pressed to get the kind of performance you need. Say now your requirement is that you have to service that interrupt within 1 millisecond. Well, on an Arduino, you're going to be hard pressed to meet that requirement. But on an STM32, you'll be just fine, because you can have, 10 interrupt vectors, and they'll get serviced very quickly, and you can very quickly then read the data from that device. So, I think you need to sort of know, it comes with experience, I think. So the other factor is, of course, cost. Can you justify the increased cost of using an STM32? Maybe not. But if cost is really no object, then you almost won't go wrong by choosing an STM32. That's a good question. Yeah, so let's forge ahead then on how we would go about designing an STM32 into our own project. They're complicated little beasts, not as complicated as some things, but they are pretty complicated. So there's a lot of configuration that has to be generated. And the easiest way to do this is with the vendor provided tools. They provide this ST Microelectronics provides this tool called CubeMX, which is basically, allows you to download the firmware for any one of their devices, any one of their microcontrollers, and you go through it and you generate, you select what features you want to use, like what kind of GPIOs you need to use, which peripherals you need to initialize, and it generates all that configuration code. Of course, you still have to write the functional code that does all the things and implements your custom logic. But this is a huge, huge advantage, especially for people who are new to this and don't want to, or wouldn't know how to begin configuring a microcontroller from scratch. So this is super useful. It also, one of the features is the, clock configuration. So you're going to choose your oscillator, because they have an internal oscillator that I've tried out once before, and I wasn't very plussed with it. I just don't think it's as accurate or consistent as they lead you to believe in the data sheet. So you'll get much better performance with an external oscillator. So if you have like an 8 megahertz external oscillator like we have in this little diagram, you can see that it's going to go through this phase lock loop, which will multiply it by 9 times and result in a system clock of 72 megahertz. That's decent. That's pretty speedy. I mean, it's not going to set the world on fire, but that's a lot faster than an Arduino for sure. And if you're looking for another thing that you'll get with with STM32 is the option to add a real-time clock, which is much more accurate for timing, like keeping real time. Well, it's exactly what it says, real time. So if you want to tell how many days have passed since you turned the thing on, for example, that's what you'll need to be able to determine that really precisely. Yeah, and again, we prefer an external watch crystal. So what kind of components or elements are we going to need in our schematic? I guess I should have made a block diagram. It occurs to me now, but the microcontroller, like we said, runs on 3.3 volts, or well, anywhere between 2 and 3.6 volts. And on our robot, we typically don't have voltages like that running around. We've got like 5 volts, 12 volts, 24 volts, stuff like that. I'd be worried about, running around 3.3 volts for various reasons. So like on NASA, we like to use 5 volts to power our sensors and whatever. So with 5 volts, a linear regulator is going to be just fine, because you're only dropping a couple volts. So you can see the above diagram here shows just a simple linear regulator configuration. And it's got a little LED to indicate that it is on, which we like. I've got simple reverse polarity protection and a simple overvoltage clamp, and this F1 over here on the left, that's a PTC fuse, or a positive temperature coefficient fuse, so that if the current gets too high through that fuse, then it heats up, and as it heats up, it increases its resistance, and it kind of acts like a fuse in that sense. Those are really nifty little things to use. So then if we had more than 12 volts, you want to start considering using a buck converter, especially like when we have, say, 24 volts like we do on NASA. The micro will probably run on a few tens of milliamps, if not less. But if you have to drop 12 volts to 3.3, that's 9 volts to drop, and that's going to dissipate a couple watts even at a few hundred milliamps. So these are sort of high level considerations to think about. And I've just thrown in a little example of what a buck converter might look like. You can see, yeah, there's a lot more parts, well, not a lot, but there's a few more parts, and it might be worth it to at that point. You got to weigh the trade-offs. If my linear regulator really can dissipate 3 or 5 watts, and if I'm okay with drawing that much power just to power a little microcontroller, maybe that's fine. Things to think about. So now here we'll continue on designing the schematic. And here I've taken a little clip from Micromouse 2020. And this was work done by Zach Baldwin. I think this is a good representation of something that you might end up with. And a question that pops up a lot is like, which pin does what? And that's where that's why I recommend starting with STM32 Cube MX, because that will start telling you like which pins are available to be used for UART, and which pins can be used for I2C and all of that. But what my guidelines are is that you want to start with those critical functions. In this case, our critical function was I2C. We needed I2C to talk to our sensors. So there's only going to be a couple sets of pins that can be multiplexed to handle I²C. So we've set up I²C first. Then we got to figure out our other peripherals, like we wanted a full JTAG debug header, and we also wanted a UART debug header. And then once you've got those basic critical functions and required interfaces, you use whatever's left over for your GPIO. And like I just said, UART headers are nice because it's very easy to just hook up a debugger to the UART header, and then you can, printf stuff, and just, it's gonna save your life one day. So put a UART debugging header on there. A reset button. Typically, reset buttons just, in the case of STM32s and in Arduinos too, the reset just pulls that pin low, and that resets the whole thing. So it's nice to have that on there. What is this? Boot. Oh yeah, the boot pins. That's something you don't have on Arduinos, but it selects, where to boot from. Whether it's going to be user flash, system memory, or the embedded SRAM. And typically, you just want to pull it down and make sure it's, you put a resistor there, so just in case you had some esoteric need for it later, you could jumper it to the 3.3 volt rail and pull it up. But typically, you just pull it down, and that's all you need. You've got your programming and debugging header. In this case, we've got a full JTAG interface, but serial wire debug, or SWD, is often all you need, which is basically a stripped down version of JTAG. So it has an IO pin and a clock pin, and that's about it. And then you can do a lot with that, including programming it. Then a very important point, you can see all these capacitors up at the top left, and you say, well, why do we need all of that? You really should have a bypass capacitor very close to every power input pin. I could spend a lot of time talking about why that's important, but I don't have a whiteboard with me, and so for the time being, just take my word for it that you really need that. So bypass caps, they're important. So now let's say you've designed the hardware, you've laid out the PCB, you've got it manufactured, you assemble it. Now it's time to write some firmware. And fortunately, it's not the end of the world, because like we said, we have CubeMX, which generates a ton of configuration code and takes a lot of pain out of our lives. And they also provide you with what's called hardware abstraction layer libraries. So it's basically just a bunch of functions that allow you to, they act like drivers for the hardware. Is this what we use for NASA competitions? It is indeed, yes. We use anything custom that we do with the microcontroller. We design a custom board with an STM32 of some kind, and yeah, it's served us well so far. Yeah. We do other stuff like embedded Linux for the hardware controller, but for low-level stuff like sensor interfaces and motor controllers, yeah. So yeah, you'll get the complete source code for the hardware abstraction layer if you want to look at it, and it's written in standard C. And you can compile in C++. You do have that option. So that can be a lifesaver too. I've also heard from one of our members, Ben Scholar, who's not here because he doesn't need to be, but he's started using Rust to program his microcontrollers. I've never used it myself, but maybe we can get Ben to give us a rundown on his work with that. But yeah, Yeah, so writing the firmware, you don't have to wait till you have the hardware either to start writing firmware. That's maybe that's sort of obvious to say, but a lot of times people hesitate writing firmware before the hardware is ready. But you can lay down some boilerplate stuff before your hardware is built. Yeah. Whoops. So now that we've got our, as we're, now that we've got all of our source code, we want to choose some kind of development environment. Previously, I used to use STM32 Cube IDE, which was based on Eclipse, and it had all these plugins that were useful, and that works fine, works out of the box. But nowadays, I'm using Visual Studio Code, and it's also not that hard to set up, so don't be scared of it. There's some user-created plugins, and you install a couple things, and you're ready to go. So, and I like the environment better than Eclipse. So if you have questions about setting either of these up, I can help answer them, or any of our more senior members can probably help you. And yeah. So then I've started, the next few slides are kind of in their proto stages, but some features that we use heavily at CWRUbotix, this is mostly talking from the experience of the NASA team. One of those examples is CAN bus. It's because we could have a part of a lecture just on CAN bus, but it stands for Controller Area Network. So it's kind of an asynchronous protocol in that you have a bunch of microcontrollers. What do those circuits do? Yeah, which circuits? I mean, you can just unmute yourself and ask the question if you like.
Oh yeah, I was just curious about like the top one and the bottom one, like I guess both.
Oh yeah, well, so these are, basically this is what provides a physical interface to the CAN bus. So like on your microcontroller, you have the logic that's required to implement the CAN protocol, but you don't have the physical hardware on the microcontroller to talk on the CAN bus. So that's what these circuits do. So you can see you've got on the right, you've got CAN TX and CAN RX, whoops. And then on the left, or at least on the top one on the left, you've got like this termination resistor, and you've got CAN high and CAN low. It's kind of, CAN bus is a really neat protocol. I have a lecture where I talk about electrical interfaces and including CAN bus in more detail, but that's basically what they do. So CAN bus is like a differentially signaled protocol. So ordinarily when you're not sending data, it's just chilling out at like, both lines are at like 2.5 volts. And then when you want to send data, the lines are pulled apart. So the high one goes high and low one goes low, and that sends a bit of data. And then, so that interface, you're running typically on a 5-volt CAN bus where the common mode voltage is like 2.5 volts. It would be tough to build that into the microcontroller. And you also want options. You want like, what if you want extra ESD protection? And what if you want an optional termination resistor? And so there's good reasons to have the CAN hardware external to the controller. Does that sort of answer your question?
Yeah, thank you so much.
Sure.
And what's the yellow box?
That's just the chip. That's the chip that does all that stuff, that takes the logic signals from the microcontroller that you can't see, and it takes those signals and puts them out on to the CAN bus. So yeah, the yellow box just represents the little chip that you're going to place on the board.
What would be a couple examples of like peripherals that would use like a CAN bus communication, like on
Yeah,
that or something?
sure. So a lot of stuff you'll buy off the shelf is typically doesn't use CAN bus, because most hobbyists are not using CAN bus. So, but examples of peripherals that use it would be like motor controllers, or we have motor controllers that we buy off the shelf for NASA that use CAN bus, and we communicate with them over CAN. That's pretty convenient. Another example would be like, say you have a, a tachometer on your wheel that's encoding the rotations, or I guess you'd call it an odometer maybe, that's encoding your wheel rotations. It might be convenient for it to talk over CAN bus so that other devices can see those messages and use them. I mean, if you want to find a bunch of CAN bus related devices, just look inside your car, and almost every sensor in there in your car uses CAN bus. That's really why CAN bus was invented, was for use in cars, because you only need 2 wires to communicate between all these devices. So it cuts down on copper usage. So car manufacturers wanted a cheap and efficient and effective and robust way to communicate between a bunch of sensors, and they invented CAN bus, and it's stuck around because it's pretty good, and it's ridiculously robust. I mean, it's robust and it's good. So it is a little tricky to, you're probably not going to find a sensor off the shelf that will use CAN bus. It's often when you're building a custom system like we do on NASA that CAN bus really shines.
That makes sense. Cool. Thank you.
Yeah, sure. Yeah. So yeah, these 2 different parts, there's 2 different little schematic clips. One shows a non-isolated CAN bus, and the other shows an isolated CAN bus. And the isolation is just if you're extra paranoid about killing your circuits, so you isolate it, and then if somebody comes along and you gotta imagine the worst case scenario, which is probably like a 48 volts getting applied to the CAN bus, and you'd really rather not have that destroy your sensitive circuits. So an isolated CAN transceiver is a good choice there. So that's CAN bus. Another thing you might use is the pulse width modulation. So it starts, in the internals of the STM32s call them general purpose timers, as its timing is how you generate PWM. So you have this, like, basically you have these counters that are getting clocked by your internal clock, and they count up to some value, and then they reset, and they count up and reset. And then you have a compare value, which might be like, somewhere between between 0 and the value that the counter counts up to. Then when it hits that value, it sends a signal to the DTG controller here, and then it signals the output control to do its stuff. So yeah, it's not as complicated as it might seem. I hope it doesn't seem too complicated. It's just a way of sending. It's how you generate PWM. Even the timers or the PWM generators on an Arduino work very similarly to this, but they're far less configurable. You can configure a lot on the STM32s. With Arduinos, you're kind of locked in to the to the frequency and resolution that they give you. Whereas with STM32s, you can adjust that resolution and also adjust the frequency so that you can get exactly the PWM you want. And some STM32 parts have, I recently found out, like recently as in the last year, found out about some STM32 parts which have a high resolution timer. And those are really, really cool. We could have a whole workshop just on how to use high resolution timers. But yeah, that is a talk for another day. Yeah, and this is in progress. Sorry, this is almost, I sort of pulled this from another lecture which I usually give about electrical interfaces, which talks just about all the commonly used electrical interfaces that you might run into. Yeah, and this is one of them, SPI bus. It stands for Serial Peripheral Interface, and it's typically it takes 4 wires. You have 1 wire that will signal the worker device. You'll signal it with the chip select line, and then you have the 3 other lines that will send and receive data. And yeah, that's almost a talk for another day, especially because this slide is in progress. And I think that's all I've got for today. Wow, it almost did take an hour. Have I been talking that long? Well, yeah, so I'd like to hear if you have any questions, any comments, or especially requests for future workshops or lectures or anything I could talk about.
I have a question regarding the circuits. So like once you made the diagram, how do you like actually make it? I'm assuming you have a printed circuit board and then you kind of just have to like do some soldering.
Yeah, so once we've actually designed it, usually you'll order the circuit. What the fuck? You'll order the printed circuit board from a PCB manufacturer. Usually we order them from China because the price is right. So we order our printed circuit boards from China, and then yeah, like you said, you solder the parts on, and yeah, that's how we do it. So we do assemble them ourselves, which is a little bit, on bigger boards it gets a little tedious, but it's totally doable. We've never designed something that we couldn't assemble in-house. Yeah.
Thank you.
Sure. Yeah, so I've got, just while we're looking at my screen, I've got this document. If you go to our top level drive and you click on resources, you can jump to this document called Quick Links to Resources. And it is what it says. You can scroll through this and find links. Some of these documents are outdated. For example, our Getting Started with Altium and the Altium Central Library. Those are currently outdated. I'm working on getting them updated. We got like design resources, which you can go to. And I've got like all these PDFs that I and other members have like found useful over the years. So those are a lot of stuff to look through there. And then I've got all the links to all the lectures, slide decks. I don't have today's lecture, so I could put it there. Yeah. All right. So yeah, this is something to check out if you want to find this slide deck. Either of these slide decks. What? Wait. Oh, I linked the wrong damn. Yeah, so that document exists, and if you want to find these slide decks, they're here. How many separate microcontroller boards do you have on the NASA robot that we designed? So do you mean like separate designs, or do you mean separate, like how many separate modules that each have a microcontroller?
I guess like separate modules.
Okay, separate modules. Yeah, let's see. Last year of what we designed, just on the robot itself, we would have had 5, only 5. This year we're stepping things up a notch because we're designing a couple things that have that are going to have microcontrollers, such as battery management system and power management system. Last year the power management system was much dumber. This year it's going to be more interesting. And then if you look at the boards that are off the robot, you know, for our localization system, that's another 3 modules right there. Yeah. So, you know, and this year we're also designing our own brushed motor controller, which is going to have a little micro on it. And that'll be fun. Yeah.
Cool, thanks.
Yeah.
If I want to like do more things with like circuits, like designing them, should I join the hardware team or mechanical team on the NASA competition?
Oh yeah, the mechanical team designs mechanical stuff, so you definitely want to join the hardware team, because we design all the electronics, or well, any electronics that we design on.
All right, thank you so much.
Sure. Electron parametric searches and reading data sheets would probably be helpful. Okay, that sounds cool. Because yeah, I mean, that's a thing yeah, I could totally do one like that. How many, could I see a show of hands of people here who would be interested in some kind of lecture or workshop about parametric searches and reading data sheets?
I'd be interested, but I mean, I'm a freshman, so I don't know if it'll be like really over my head or not.
It won't be. I promise it won't be. Like,
Okay, cool.
it's like using Google but better.
Nice.
Like, I mean, my preferred, I think the website that has, well, I don't know if we want to right now, because it could be a whole lecture, but
Yeah, definitely.
DigiKey is a nice, is my preferred website. They don't always have the best prices, but they do have, in my opinion, the best parametric searches. So the DigiKey is good for parametric searches. And besides, if we're spending the robotics team's money, it's not really a big deal. But if it's my money, I buy from Mouser.
I'm not sure really what parametric searches are, but it seems
Yeah,
cool. It'll be something I'll be interested in.
Sure. Well, I mean, I could answer that easily. This is a search, and up here are all the parameters in all these different boxes. You can see there's like 20 parameters. And, you know, some of them you don't care about, some of them you do. And so that's a parametric search.
Okay, thank you.
Yeah, sure. Well, it's about 5, and I've got to get to our NASA meeting if it's still happening. Did you do basically unusable? Well, Wi-Fi, internet. Well, PDM, blah blah blah. Okay, well not. Okay, it looks like we're not doing the meeting. Okay. Sounds good. Well, All right, well, thanks. Did I major in electrical engineering? I did. I'm majoring in electrical engineering now. And I'm not graduated yet. I'm still a student. All right, well, let me at least stop recording this because I think we're